Hello everybody and welcome to week 10. I'm all excited because that is double digits and that means that we only have a few weeks to go. So we're moving on in our curriculum, and this week we're going to talk a little bit about multiplying monomials. We already talked a tiny bit about that last week. We're going to finish that up. Monomials. And we're going to talk about binomials, multiplying binomials. And again, we talked a tiny bit about that last week, but I want to make sure that we get a little bit of actual notes in here. So the first question I wanted to ask today was, what is a monomial? And when you see that mono, that generally means one. So this is one term. So we're multiplying things with one term. And this, the bi there, means two. So two terms. Okay. So last week we talked about, hey, we're using algebra tiles or Algeblocks to do some multiplication. And we're going to have something that's the quadrant map, if you remember that. It looks something like this. 4 quadrants, a positive and positive and a negative. And on top of that, a lot of times we're going to use a factor track. Now, if you don't have a factor track because you're not here face-to-face with me, it's okay, no big deal. But what it means is you're going to have to use the track here to line things up and be a little bit careful about it, right? So I'm going to use the factor track to put my factors on it. That factor track is going to go right where the x and the y axis are. And then if you remember, excuse me, the process that we're using here is the rectangular area model. So hopefully at some point you may have seen the rectangular area model. And basically it means if I create any kind of rectangle, then I know that I can find the area of that guy by multiplying the length times the width, right? Okay. So for us in our particular situation here, where we're using Algeblocks to show students how to do some multiplying and some factoring. For instance, I remember when I was teaching high school that one of the problems on the EOC STAR exam for Algebra 1 was so factor this trinomial using Algeblocks or algebra tiles actually, and the students had maybe 4 pictures, and it might say which is the best depiction, or it might say if this is the picture, then what would go on the track here, things like that. So the students had to be able to look at the algebra tiles and figure out what the x and the x squared and the ones were, and all of those things. So to remind us real quickly, we have for our Algeblocks, we have these units, right? Those are worth 1. We have a long like this, and that is worth an x. We call him an x. And then we have a, basically like in base 10 blocks, we would call that a flat, and he is an x times an x, so we would call him x squared. So I'm going to be modeling with Algeblocks, but you were asked to have algebra tiles at home. So just to make sure we're all on the same page with that and we can compare, that was one of your participations before the exam. These are my units and my algebra tiles. There's an x, or my long kind of guy. And here's a square, large square, or a flat if I were using the base 10 terminology, and he is again x by x big, right? So they end up looking similar, but some of the differences you guys told me on your participation was the algebra tiles come with a negative built in. So everything could be a positive or a negative. If it's red, we know that's the negative case, right? Okay, if it's one of the other colors, like here, now I have a positive x squared showing. Here's a negative x, a negative x, negative 3, right? So if that's the case, then I have that. So for your algebra tiles, you don't actually have to have an algebra mat, but I'm going to ask that you use the mats. So I loaded up the large mats, similar to what I'm using here in D2L, so that you could see those, so that you could use those. So whenever you do your video in a couple of weeks, I'm going to ask that you actually have that large one so that you can put your actual algebra tiles or Algeblocks onto the mats so that they're size appropriate. It would not work for you to use the little bitty mini mats and then to have the larger algebra blocks or Algeblocks or algebra tiles. Okay, so with that in mind, I'm going to demonstrate with Algeblocks, but you should be able to follow along with your algebra tiles. The coloring may just be a little bit off, but it's not that big of a deal. And the reason I'm doing that is because my Algeblocks will actually fit in the mat and fit in the factor track very nicely. So here was my quadrant mat, there was my factor track, so that's kind of the idea. We already did some problems. Let me zoom out just a tiny bit here, sorry. It does that autofocus thing, sorry. I just want you to be able to see the entire mat here. We already did some problems last week where we talked about multiplying and the different things that happen. So for instance, if I just give you an example, let's say that I want you to work the problem. Let's do 2x times negative 3x. And I want you to show me what that looks like. Then you're going to be able to say, hey, one of these is my length, one of these is my width. It doesn't really matter which one goes in which factor track. They're all x's, so it's not as if it's really an xy track. It's really the factors that are going in there. So we'll see what happens in there, and then we'll multiply it out. So I've got a 2x. Let me see it again, sorry. 2x times negative 3x. So, and it doesn't matter which direction goes where, it just really matters that I pay very close attention to my negatives, if that makes sense. So let me zoom out just a tiny bit more, I'm sorry. I can't see the bottom negative here. Here we go. There's the negative there. So here is a positive. Here is a negative on this track. And then on the up, down, the vertical track, it's positive going up, negative going down. So I need a positive 2x and a negative 3x. It doesn't matter which one I put it on, except that if I put, for instance, the positive 2x there, I can't put the negative 3x down here, right? And I can't do that because, why? It's not making a rectangle. Does that make sense? So even though this is a positive and this is a negative, I'm not making a rectangle. And the whole idea is to make a rectangle so that I can figure out the area of the rectangle, right? So if I put the positive 2x there, then I need to make a rectangle. I need to put the negative 3x here, right? If I'm going to do that, okay? Some people, they want to keep their y's positive. That's fine. So we would fill in over here and see what we have. If you don't like that, if you want to always start on what we traditionally think of as the x-axis and make that a positive 2x, that's fine. But again, I can't leave the negative 3x over here because it doesn't make me create a rectangle between them, right? It's just a straight line. So if you want to put your positive 2x over here, that's fine. But where does the negative 3x have to go? Yeah, down here on this factor track, right? Negative 3x. Okay. So if you're going to do that, just be aware that it does make a difference where you're putting things. All right. So I think I'm actually, just because I'm kind of out of space here and it's crammed down there at the bottom, I don't think you guys can see it. I'm going to put my big negative 3x over here because I know you can see that on the camera. So here's my positive 2x going up, There's my negative 3x going over there. And now the idea, remember, is to make a rectangle. And it's really important, remember we said all of my break lines here, wherever this x breaks here, that's where I want everything to break. Which means I'm not going to fill this guy in with a bunch of units, right? Because for one thing, they don't line up at the end. I want them to start and end at the same point. And for the other thing, this break line here in the unit isn't showing in this X. So it doesn't make sense to put little unit guys in there, right? So don't do that. I could use the X's. That would line up and down, right? But does it line up side to side? The breaks, where are the breaks? No, it's not lining up on the breaks here, right? So it would be like 3 of these across, and again, notice it doesn't actually line up. It's a little bit wonky there, so we're not going to use that. It does line up here on the top, but not here on the side, so we can't use the X guy. So what do we need? We need a piece that is X units tall and X units wide. Well, we know that's what? X times X is X squared, right? And again, look, the break line here matches and the break line here matches. So you want to make sure that whatever rectangle you're creating, it's going to line up with all the breaks. This one, again, it's an X times an X. So I fill it in with an X squared. Okay. Here, again, it's going to be an X times an X. So that's an X squared. All right. Okay. And once I do it for this X, it should be pretty clear that this X times this X is going to work the same way. X squared. X times X is X squared. X times X is X squared, right? So that should work out pretty close to the same way. Hopefully it's not too terribly out of the way, out of line, and we can see how it works, okay? So if you weren't sure, what is 2x times negative 3x? Remove your factor track, because that's part of the problem, right? That's not part of the solution. And I look and I say, well, it's 1, 2, 3, 4, 5, 6, 6 of these guys. And these are worth what? X squared, right? So it's 6x squared. And then I look at it and I say, kind of as a last resort, okay, and do I need to put a sign on it? A S-I-G-N, positive, negative. Yeah, because it's in a negative quadrant, right? There's my negative up there. So it is a negative, so this should be a negative 6x squared. That's what that represents, right? And remember, we talked about it last week. If it was over here, that would have been a positive 6x squared. But it's not. Oops, lost my x squares. It's not. It's over here in quadrant 2, and in quadrant 2, anything that's in quadrant 2 here for me is a negative. Okay, so negative 6x squared. And when we come back here and we work this, as adults, of course, we know it's 2 times 3, negative 3 is negative 6, and x times x is x squared, right? Okay, so that was a monomial times a monomial, one term times one term. And it doesn't have to have the x's in it, right? Is everybody okay with that? I hope so. What if it was just like 5 times negative 3x? 5 times negative 3x. So I'm going to start that one out the same. I'm going to keep my negative 3x over here on the negative track, but instead of these 2 x's, I don't need them anymore, right? I need a 5. So what's that going to look like? 5 little units right there in the track, right? So here I go, 5 little units. Line them up nicely. Okay, so this is the problem, 5 times negative 3x, as displayed in Algeblocks, right? 5 times negative 3x. Well, if I'm going to fill that in, then I need a piece right here that is 1 unit tall or wide by an x unit long, right? Well, what is that? 1 times x. It's 1x, right? So I'm going to put it in there. I can't put it like that though, right? That's a problem. I need all of my break lines to line up. So I'm going to turn him sideways. He ends here. He ends there. He lines up nicely with the green going upward and the X, the yellow X going side to side. So I need to fill that in. One of the problems as we look toward, you're going to have an exam on these, is that if you haven't noticed, most of the Algeblocks and algebra tiles, the sets are not very big, right? So I'm going to have to keep with relatively small numbers. Okay. So does everybody agree that each of these breaks at the same point going up, and they all break at the same point coming down, and that matches up with what's in the question? Okay. So what about here, this guy? He needs to be 1 times x to fill in that rectangle, right? Okay, so, and same thing all the way up, right? 1, 2, 3, 4, 5. I think I've got 15 of these. I need 15, right? 3 times 5. Okay, 1, 2, 3, 4, 5. All right. And as I look across there, all of my break lines are matching up. I can pull the problem off. I don't need that factor track anymore. That's just to set the stage, so to speak, to see what is the question that I'm answering. And I look at this and I say, is that a rectangle? Well, yes, it is a rectangle, right? Everything starts and ends. Those are straight lines. Straight, straight, looks good. And so I say, what's my answer? 15x, right? Okay, there's 15 x's there. But then I need to say to myself, what's the sign on that? Is it a positive or a negative? Negative, right? Because it's in that quadrant right there. So the answer here is what? Negative 15x, right? Okay, so the physical, what should be happening here is the physical model that we're creating at this point should match up with the more abstract multiplication that we know we should be doing here, right? So we, as adults, again, know 5 times negative 3 is negative 15. There's nothing there as far as variables, so it's just the 5 times the negative 3x, right? So negative 15x. So hopefully that looks a heck of a lot like negative 15x, what I have here as my answer on the quadrant mat, right? Yes. Okay, so that being said, let's just do 1 or 2 where we go a little more advanced. Remember that I think I talked about last week, what if it was something like 2 times x, let's do x plus 5 first. Okay, 2 times x plus 5. So here comes my mat. I'm going to get everything off my factor track. And I'm going to do 2 times x. I'm going to go up with the x part of it. X plus 5 is what I said, I think. 2 times x plus 5. Problem with me videotaping, I'm covering up what I'm doing, so to go back to it. All right, 2 times x plus 5. All right, again, I kind of ran through this really quickly last week. We're going to spend a little bit more time on it, make sure everybody can do it. Again, the really important part here is that things need to line up. So here I'm doing a 1 times an x, so what piece fits in there? The x, right? Lines up right there. So if you're watching me doing this and you're like, okay, I get what she's doing, that's okay to get what I'm doing, but then you really need to be doing this yourself too. So maybe pause the tape, pause the recording. I know, my old tapes. Pause the recording and say to yourself, what piece fits in there? It needs to be 1 block wide, 1 unit, and 1x tall. So it needs to be a 1x. 1 times x is 1x, right? So see what you can fill in with. For instance, right here, what piece needs to go right here? It needs to be 1 by 1, right? 1 times 1 is 1. So see if you can fill in here and see if you can make a rectangle form and do it with your own algebra tiles and then see if what I come up with looks the same as what you have written down, right? So I'm just going to plop up my answers here. I think that these should all be a bunch of 1 by 1 cubes, the little tall cubes, the unit pieces. So it's really, as I think about it, 2 times 5. And 2 times 5 is 10, right? Okay, so I put 10 little unit guys in there. That's what I have going. And again, does it break the same going up and down? Yep, everything's breaking in the same spot. Does it break the same going side to side? Yep, everything's breaking in the same spot. What I wouldn't want to see is I wouldn't want to see something like somebody put an X here, right? Even though it might actually end up that it's about the same length, it's not exactly the same length up there, right? You can see that, I think, that it doesn't really line up. Even though it might end up about the same, you've got a problem here with things. Where do these horizontal lines break? Well, on the green guys, they break here and here and here. But if you stick that yellow guy in, they're not breaking at the same spot, right? So don't do that. And what you'll find is a lot of times each of your smaller rectangles is going to be the same color. And what do I mean by that? Here there's a smaller rectangle and they're all yellows. And they're all X's, right? Here there's a smaller rectangle, they're all greens. Or all units. So kind of start thinking about those a little bit. I think that here I've got it. All of my break lines are matching up. So I'm going to remove this problem. I'm just going to have my solution, and I say to myself, is that a rectangle? Well, yeah, that's a rectangle. It's a long, skinny rectangle, right? But it's a rectangle. And then all I got to do is say, okay, so what is it? And notice again here, I'm in the positive quadrant. So I don't really need to worry about my signage, positives or negatives. Everything's going to be a positive here, right? Okay, so I've got 2x. And then I've also got positive 2, 4, 6, 8, 10. So I've got 2x plus 10. That's what my answer is on the model. Okay, and that stinking better line up with whatever the math is here in a second when we do it abstract. But I think it's 2x plus 10. That's what I've got. So if you were to distribute this through, sure enough, you'd get 2x plus 10. They're all positive, just like what I had. So, hey, we're doing pretty good, right? That looks all right to me. Okay. So, I'm going to put up a binomial times a binomial. That was a monomial times a binomial. So, a binomial times a binomial. You guys work one out. I'm going to keep it all positive for a second, and then I'll run through it real fast and make sure that mine matches yours. So, I'm going to do x plus 3 times x plus 5. So if you need to stop the tape real quickly, let's see what that looks like. I'm going to go ahead and work through mine. But if you want to practice and make sure you can get it, here we go. I'm not going to slow down. So I've got the x plus 5. I need an x plus 3 on this side. And then I'm going to make sure that all my breaking points line up. So x times x is x squared. Right here on top, I've got an x times a 1 going up. So that looks to me like those need to be x's so that my breaking will line up. I'm also checking as I go this vertical break here. It needs to be the same, which means that I did a good job keeping all of those x's. Okay. Here on the side, it's an x times a 1, so I feel like this is an x. This is an x, and this is an x. So again, here the horizontal line, it's breaking at the same point. The verticals are breaking at the same point. I feel pretty good about this. The problem is whenever I look up here in the top piece here, that's a 1, 2, 3, 3 times 5, right? What should be filling in there is a bunch of 1 by 1s, right? Because it's 1 by 1. So as I look at that, I say, hang on a second. That should be a whole bunch of green guys filling in there. And in fact, we know 3 times 5 is 15, right? So if I was really doing well, I would just say, hey, that's a 3 by 5. That's a 15 square centimeter, basically, rectangle up there, and I would be doing good. Okay. So now I say, hey, I've lined everything up. All my breaking lines line up. Let me remove the problem. I don't need you anymore. Just please be careful not to count whatever is on your axes here. That's part of the problem, not part of the solution. And I've seen people confuse themselves a lot by leaving that on there. So when I say I'm going to remove the problem, if you're just laying them out here, then remove those pieces so that they won't confuse you. So as I look at this, I say, okay, that's x squared. It's all in the positive quadrant, by the way, right? 1, 2, 3, 4, 5, 5x. 1, 2, 3, 3x. 5x and 3x is 8x. And then this is all 15. We counted a minute ago, right? So let's see how that matches up, because that's x squared plus 8x plus 15. Let's see how that looks. Again, we're going to multiply, distribute this guy through, right? X times x is x squared. X times 5 is 5x. 3 times x is 3x. And 3 times 5 is 15. Now notice for just a second, if you have done any of our math ed classes at the lower levels, the 350, the 351, then you will see in here the partial products, right? X times 5 is 5x. X times 3 is 3x. Okay, we're going to combine those like terms in a minute, but before we do that, let's look again real quickly at my model. There was a 5x, right? And there was a 3x. So remember what I said earlier, all of your smaller rectangles should line up. Not only should all your smaller rectangles line up, but they should represent your partial products that are in there. So one of my partial products is x squared, one is 5x, one is 3x, one is 15. And sure enough, there it is, x squared, 5x, 3x, 15. Now we know that in a second we're going to combine all those like terms. X squared plus 8x plus 15, and that's what we're going to get, right? Using the abstract. Using the actual model, all we would do is say, hey, I've got that x squared there. Let me pull all these x's together and literally combine my like pieces, and sure enough, there's 8 of them there. And then the 15 would be by themselves again. So my model does match up, which is good. We want that to happen, right? All right. And then real quickly, let's go back and do one. I mentioned the other day, what if one or both of these were negative? What did that do to us, you remember? So I'm going to keep it in x plus 3, but we're going to do x minus 5. X plus 3 times x minus 5. Okay, so I remember that whenever I made one of them negative, that makes me go into a different portion of the mat, right? A different one of the quadrants. So let's see. X plus 3 still looks like x plus 3, right? And that just needs to be the only thing that's on this particular axis. So to do x minus 5, for instance, I'm not going to put the negative 5 over here, right? Because that would be like x plus 3 minus 5 all as one factor. Instead, I want one factor is going to be the horizontal, one factor is going to be the vertical. So to do x minus 5, I need to do positive x, because x is positive, right? And then minus 5 is going to put me down here in the negative part of that track, right? So that portion of that factor is negative. So now we're looking at it. It's going to work out very similarly. Up here, I'm still lining up my brakes. I want to know what things are going on here. So there's an x squared. What happens here? 1 times x. That's an x, right? And it's going to go 1, 2, 3 of them, right? I think we're getting, hopefully by now we're getting a little faster at it. Okay, so on the top, I'm good there, x squared plus 3x. That's kind of the same stuff I've been doing, right? But now I'm thrown down here into basically what's quadrant 4, right? I still need to line everything up, but I need to realize anything that I put here is going to be negative, right? So that's going to make for funny stuff happening here in a minute. We haven't done one like this yet, so this will be useful for us. Okay, x times 1 is x, and there are 5 of them, right? And then what the heck's going on here? Those are those 15 singles still, right, that we had before. A 3 times a 5, still a 15. But now they're what? Negative. So let me fill this all in. All right, so look real quickly, make sure they all start and end at the same point. Make sure that all my break lines line up all the way across, vertically, all the way up and down, horizontally. Yep, I think it's good. Take the problem off. We don't need to see those problems anymore. We know what they are. And what I've got here is x squared plus 3x. But what happened down here? Those are all negative now, right? So it's minus 5x and what? Minus 15. Okay, so hold that thought for a minute, because first I want to make sure that it FOILs correctly, or distributes correctly. Okay, x squared minus 5x plus 3x minus 15. Okay, so that's what we said. I'll put it back up in a second so we can see it. X squared, I actually said the plus 3x, but that was my inside guy, so he took me a little longer. But x squared minus 5x plus 3x minus 15. So plus 3x minus 5x minus 15, right? Okay, that's an x, 3x. All right, so again, we've got our partial products, but what the heck's happening here? Yeah, we're still going to combine like terms, but we know there's a negative and a positive there. Let's do it real quickly so we know where we're headed as adults, and then we'll see what it looks like for the kids. So x squared minus 2x, right? Because negative 5 plus 3, we subtract, take the sign of the bigger number, add the x on the end, right? Minus 2x, and then minus 15. Does everybody agree? Check my arithmetic. X squared minus 2x minus 15. All right, so here I am. I've got the x squared plus 3x minus 5x and the minus 15. How in the world am I going to make that happen? What was that subtract thing going on? When they have opposite signs, we subtract them and we take the sign of the bigger number. Well, we need to be able to model that here on the map. Show how in the world does that happen? And the idea comes back to something we did last week. I'm going to move these 15 out of the way. Okay. The idea comes back to what we came up with last week, which was that concept of 0 pairs, if you remember it. Okay. So as I'm looking at this, I see, look, there's a positive x and there's a negative x. And what in the world would happen to those if I added them out? Plus x minus x is a 0, right? They're going to 0 pair out. I'll stick them right here so we can see them. They'll 0 out so that they'll really go away, right? Here's a plus x. Here's a minus x. Again, they'll 0 out, right? And one more time. I need a little more space, sorry. Plus x, minus x, they'll 0 out. So what we really have going on here is a positive 3 on the top and a negative 3 on the bottom, and those are reducing out. They're making 0 pairs, because we all know positive 3 minus 3, or in this case, positive 3x minus 3x, it doesn't matter. The concept is the same, whether I have the x stuck on the back or not, right? So positive 3x minus 3x, those are 0 pairs, and they're all going to 0 out, and they're all going to go away. So what I'm left with is going to be the x squared. And the reason why the negative guy wins, so to speak, this battle, whenever I'm doing negative 5x plus 3x, is there's just simply more negative guys left around, right? Once they all 0 pair out, there's still negative x's left over. So my answer has to take the sign of the bigger number, because there's just more of them sitting there, right? Once all my 0 pairs go away, there's extras down here. That's what that means. And the negative 15, of course, is just hanging around. There was nothing for it to 0 pair out with, right? So my answer is x squared minus 2x minus the 15. That's what we said we were going to get. But now we have a physical model that shows us what the heck is going on there, right? So we can see, where did that come from? All right. And last but not least, the most difficult of these would be, what if there was a negative, or more than one negative, but I'm just going to do one negative in each of my factors. And again, we're going to do the same x and 3 and x and 5, but I'm going to make them all negatives. Okay, x minus 3, x minus 5. Just the whole numbers are negatives, not the x's. Okay, so again, let's do this real quickly. Just working out the math. X squared minus 5x minus 3x, negative and a negative. 3 times 5 is 15. Plus 15, right? Negative times a negative is a positive 15. So when we finish this process, we should see a couple of things coming out. We should see, okay, how in the world are we getting, here they're both negatives. What would be the process for combined like terms? Negative 5x minus 3x, negative 8x, right? So the rule, so to speak, is when they have the same sign, you add and then take their sign, right? So this is going to be negative x. Why does that come about? And then also, where the heck did this positive 15 come from when it was a negative 3 times a negative 5? So we're going to see kind of the model taking place here and helping us out with that. We all know this is going to be x squared minus 8x plus 15. All right. So again, I kind of just expect you to be able to do this, but I don't necessarily expect you to do the Algeblocks until we show it. So, all right, that's what we're after. Here we go. I've already got the x minus 5, so I'm just going to move these 3's over here. So does everybody agree, first of all, that what I have represented here on my mat, on my factor track, is x, positive x, minus 3. That's one of my factors. And positive x minus 5, that's my other factor. Okay, I don't think we did one of these last week, or if we did, I just stuffed it at the very end, because what happens here? Yeah, whenever I fill in these rectangles, I'm going to have something to fill in here, something to fill in here. Remember, the idea is make rectangles, something to fill in here, and something to fill in here, right? So I'm going to have an answer, a solution that goes into all 4 quadrants. So again, filling in very quickly. I feel like y'all are probably pretty good with this by now. X squared in the first quadrant. X times 3 here gives me 3x in the second quadrant. Down here in third quadrant, those are only green times green, right? So there's 1 by 1 blocks. So that should be 3 times 5. And that'll give me 15. So notice that as I do this, all of my little partial products are actually the same. They have been the same ever since I started doing the same binomial times binomial, but just changing around the positives and the negatives. So I've still got the 15, but now they're down here in quadrant 3. And what goes here? It's a 1 times an x, right? So 1x. But it's really a 5 times an x, which tells me I need 5x, right? So 1, 2, 3, 4, 5. Okay, so again, look at my picture real quickly. Do I think that that's a one big rectangle? Yes. It's actually kind of interesting because when I pull the factor track off, the problem's going to go away, right? The factors that I'm multiplying. And you could think of it as 4 small rectangles. If you did, those would be your partial products. Or you could shove it all together. Just be careful that positives stay on the positive side and negatives stay on the negative side. And when, I'm not doing a very good job of shoving it all together. Sorry. There we go. And when I do that, we could see, hey, it really is, they really are a rectangle, right? The dimensions on the top are the same as the dimensions on the bottom, and so on. So everything does line up as far as my breaking lines. Yep, that's all good. So I feel pretty happy about this. So I can move it back into their own quadrants and feel like, yeah, everything really does line up. Okay, so if you're not sure, take out the problem. Don't leave the problem in there because you don't want the problem in the middle of your solution. It's not going to work very well. And then look and see, yeah, these really are. Okay, I've got x squared, negative 3x, positive 15, and negative 5x. Just real quickly, I'm right here. X squared, a negative 5x, a negative 3x, and a positive 15. Everybody agree? Negative 3x, negative 5x, positive 15. Because it threw itself into the third quadrant, right? That was negative 3 times negative 5 made a positive 15. So you can see where that was on the x-axis. The negative times the negative gave me a positive, making that rectangle there. Okay? And then the other thing I'm going to see here is, hey, hang on a second. I've got x's, and they are the same size, so I should be able to combine like terms. Do I need to make 0 pairs like I did a second ago? No, why not? Are any of these x's opposite signs? No. If there were some up here in quadrant 1, yeah, I could cancel those or reduce those with quadrant 4. Or if there was some over here in quadrant 3, I could move those against quadrant, well, either one, quadrant 2 or quadrant 4, right? But they're not. They're all negative. So I can literally say, hey, when I go to combine these, they all have the same sign. Let's just shove them all together, right? And that's going to make 8 of them, and they're all negative. Negative 8x. So now I can see the negative times the negative puts me into the positive quadrant, and I can see even though there were negatives up here and negatives down there, they're still combining like terms. They're still the same size piece, and they had the same sign. So I don't need to make 0 pairs. That's why I don't need to subtract. Whenever they're opposite signs, like if there were 2 up here, then yes, I'd want to line up some 0 pairs and move those out, right? But they're not. These have the same signs, so they all just kind of line up together. They're not canceling, they're not reducing. None of that 0 pair stuff. So that's where that answer comes from. All right? I hope that makes sense. And again, I'm just keeping things kind of nice here. I've got 1x, 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 all that kind of stuff. Everybody realizes, I hope, that, for instance, if I wanted to make this problem into 2x minus 3, oops, let me get rid of that. Sorry, 2x minus 3, then it would just be a simple matter of extending this factor to 2x minus 3. Or I could make this 3x minus 5 by just extending this factor a little bit higher. And now we'd have to still fill in all 4 quadrants worth of rectangles, but we would see what's coming, and we'd be able to work with it, right? So you're going to see that in your homework. Yeah, just remember, looking at it in your homework. And I think that you should remember what the whole point here is. There's 2 things in this particular video. One is you're making rectangles. The other point is to make sure that as you fill in your rectangles, that all your breaking points, like the x times the x, those line up, right? So one of those will be your participation. I don't know yet. We'll see. All right, so that's the idea of multiplying monomials and binomials. We started it last week. Now we're finished. And then day 2, we're going to go on and we're going to do division. Yay! I don't think we did any division last week. So next up, division.